that Richard will live a very, very long time. It's a big responsibility to continue the tradition. So he will talk about remarks on the classification theorem for finite groups.
Finite simple. Thank you very much. Thank you for the invitation to speak here at this seminar. I apologize for sitting down, but I find standing up for lengths of time is inconvenient. So, I'm not an experimental mathematician, and I don't pretend to be. So, nevertheless, any mathematician does some experimenting at times, and it's often the most fun thing to be doing. So I will at least point out some places where some experimentation of some kind went on. I want to dedicate this talk to two of my colleagues who have passed away in the last 3 or 4 months. Charles Sims died last month. Mike Onam died in August. There's a pattern there that I hope stops. Both of these fellows were my colleagues for 40 years or more, and their contributions to the theory of finite groups are extensive and deep, and we miss them. So I may get off the track. I definitely will get off the track at certain points, and one of the reasons I'll get off the track is to try to show you some of the things that these men did. So here's my outline. I'll get as far as I can get before the bell rings. Introduce the known finite simple groups, and the word known is at best ambiguous. Then a question that I often get asked, how do you even get started classifying simple groups? Unfortunately, there are some reasonably simple and partial answers to that question, so I thought that might be a good thing to talk about. Another question that I get is, how were the sporadic groups found? Also, why were they found? It did go 100 years. There was a 100-year gap between the 5th sporadic group and the 6th sporadic group. And finally, to the extent that time permits, I'll talk about the strategy and the classification. I'm trying not to do anything particularly technical, but technical is in the eye of the observer. So here's some notation. It's all standard. And all groups discussed or imagined are finite. That's a false statement or a debatable statement unless they're obviously infinite. If they're not obviously infinite, then they're finite. FQ is the field of Q elements, and bracket X is the subgroup generated by X inside some ambient group. So I decided not to go back to Galois, or even further, but to go back to the late 19th century and the theorem of Jordan and Holder, which was originally stated, I understand, by Jordan incorrectly, but he corrected it himself. He had subgroups here instead of normal subgroups. I've seen that mistake in other places during the course of my teaching career. Every finite group has a composition series. The multi-set of isomorphism types of the composition factors depends only on the isomorphism type of G. This inspired Hodler to propose a program to understand all finite groups by first understanding their composition factors and then understanding how they get put together. So you could phrase it, well, let's construct all finite groups. We'll first construct the simple ones, and then we'll figure out all the ways to put them together. not so easy. Here's an example. Suppose all of the composition factors have the same prime order P. They're just cyclic groups of order P. So that the whole group has order P to the n for some prime P and some natural number n. The only simple group of order P to the n is the cyclic group. So those are our composition factors. And here's the bad news. Let f of P to the n be the number of isomorphism types of groups of order P to the n. Then that number is roughly P to the 227th n cubed. And interestingly, the limit is uniform in P. The difference, or the ratio of the two sides, tends to what it's supposed to, independent of P. That was Charlie Sims's thesis in 1965, which I find interesting because his thesis advisor was my thesis advisor, who later told me a word of serious advice, which was to stay away from groups of order P to the n. So I'm not sure whether Sims did that on his own initiative or Thompson had suggested it. Anyhow, let's get to the main characters of the story. The alternating groups have their origins I've not delved into, I'm not sure. They certainly go back very far in consciousness, and the cyclic groups are sort of hardwired into our brains. So there's two families of finite simple groups. And already, the word known has to be in several sets of quotation marks. We do not know the alternating groups. We do not know, for example, what all their subgroups are. If we did, we would know what all finite groups are. So, what known means is a complicated question, and it's also time dependent.
But doesn't the classification theorem tell you what all the groups are?
No, just the simple groups.
But aren't all groups composed of simple groups in some sense?
Yes.
Yes.
Yeah. And all P groups are composed of groups of order P. Extension, it turns out that of these two pieces of Holder's program, the easy one is the first one. The second one is really hard.
So this
If you go about it this way. I'll show later that there is a way of getting around this to some extent, to a great extent. Then there are the groups of Lie type, which originally came up as classical groups, matrix groups. PSLNQ is a typical matrix group. It's the special linear group, n by n matrices over the field of Q elements of determinant 1. And the P means it's projectivized, which means instead of it acting on a vector space of n dimensions, you should think of it acting on the projective space of n dimensions. And in that sense, the scalar matrices disappear and get factored out. There are 6 families of such groups. PSLNQ is one of them. The 6 families are doubly indexed. You get all the other 5 by taking a vector space and endowing it with a structure of a bilinear form or a sesquilinear form or a quadratic form. One nice thing happens over finite fields, for instance, if you study orthogonal groups over the reals, there are lots of different orthogonal groups, depending on their well, Sylvester's theorem tells you how many there are. Over finite fields, there are exactly two kinds of orthogonal groups over any particular finite field. There are only two, essentially two equivalence classes of non-singular quadratic forms on a finite vector space. Then beyond the classical groups, L.E. Dixon knew about groups he called E2 of Q, E for exceptional, which is usually called G2 of Q these days, coming out of Octonian algebras and connected with the Lie groups of type G2. And there are several families of exceptional groups of Lie type. There are 10 infinite families. They're singly indexed just by the size of the field. Q is always a prime power. It's the cardinality of a finite field. In the 50s, in the 1950s, Chevalier and Steinberg gave constructions of all of these groups in a fairly uniform way over practically any field. There are certain of the exceptional types which are kind of testy and only exist over certain fields. But the rest of them can be defined essentially over any field, including the algebraic closure of the finite field. And when you take the algebraic closure of a finite field and take one of these groups over it, it acquires the structure of a linear algebraic group. And the theory of linear algebraic groups is a very detailed, rich theory. Inside that linear algebraic group sits the finite group. The topology becomes the discrete topology, which is not very interesting. But there is a lot to be learned about the finite groups by going up to the algebraic group and then coming back down. And then the last, so that's 16 families I think we have, plus 2 is 18. And then there's the finite family of 26 sporadic groups. Émile Mathieu discovered the first 5 in the 1860s as symmetry groups of differential equations. And then 100 years later, in a remarkable burst, 21 other sporadic simple groups were discovered. Actually, 22 were discovered for a very brief period of time until it was proved that 2 of them were the same.
So where's Ly?
It's in between the 4th and 5th dot. J1, I've put these down for a reason. J1 was the first one, discovered by Zvonimir Janko in 1965, capitalizing on a colossal error by John Thompson. I'll talk about that later. And Janko also found the 26th one, J4. He found 4 sporadic groups. HS is Higman Sims. Sims had a part in the discovery of that group, but also a big part in the construction of a number of the other groups, because he was a master at machine calculations involving permutation groups, as well as matrix groups, but principally permutation groups. Onan discovered a group that was one of the last ones, and the biggest one, the most famous one, is the monster. But Onan was really done in this building. Onan predicted it, Sims constructed it, Sims students also helped in the construction, Steve Andrilli. And that was all done in Hill Center. There's no plaque. So as I mentioned, the original existence and uniqueness proof for several of the sporadic groups depended on electronic calculations, chiefly coset enumeration, but doing coset enumeration, if you're familiar with the procedure, you need to have a presentation a proposed presentation for the group by generators and relations. And you may not know that whole presentation once you start. But once you start doing the coset enumeration, I remember listening to Sims discuss an interactive feature where the coset enumeration would fail to terminate and therefore fail to prove anything, and maybe because he didn't have enough relations, but he had an interactive feature where he could experiment with adding extra relations and seeing if they stood up. Some of these groups were constructed as matrix groups. J4 was constructed as a small matrix group of 112 by 112 matrices over the field of 2 elements. The hardest one of these groups to construct seems to be the Onam group, which is a 45-dimensional group over the field of 7 elements. That's hard to compute with. I'm not sure whether by now it has been constructed that way. It was constructed originally as a permutation group on 100-some thousand letters. So those are the sporadic groups. The names of Fisher and Grice go with the monster, of course. And of these groups, 20 of them can be found inside the monster in some form or other, either as a subgroup or a subquotient. And then there are 6, what did Grice call them? Pariahs. 3 of the Yanko groups are pariahs, the Onam groups are pariah, the Ruvalis groups are pariah, and I'm proud to say the Lyons group is a pariah. Now, what do we know about these groups? Well, one thing that's very important to know about them is their automorphism groups and the isomorphisms among them. It's easy to come up with problems where you can determine all the objects, but it's very hard to determine which ones are isomorphic to which ones. But in this case, going back to a paper of Emil Artin, it turns out not to be very hard to decide when 2 of these groups have the same order. And then it's not too hard to decide which ones are actually isomorphic. There are very few that have the same order. Very few coincidences. There's one solitary coincidence, and then one family has the same order as another family, and that's it. What else do we know about these groups? We know a lot of local information. I'll explain later what I mean by local information. A good deal is known about their representations over fields of characteristic 0 or fields of finite characteristic, but there's a huge amount that's unknown about their representations. And Professor Tiepp is an expert on the huge amount that's known and the huge amount that's unknown as well.
No, but Conway and Norton and other people had their atlas of the groups with character tables.
That's
all
all.
of them. So
That's characteristic 0.
Oh.
That's all characteristic 0. There is now there is an atlas. There are modular atlases, but the information is not nearly so comprehensive. By modular, I mean over finite fields. Another subject that's known, there's quite a bit known about, is what the maximal subgroups of these groups are. And that's been an area of great activity in the last 25 years. And finally, all the covering groups of these groups are known. This is sort of an inside fact. It's much harder to figure out what the covering groups are than to figure out what the automorphism groups are. To figure out what a covering group is, you have to do a cohomology calculation. And there are several tales of groups having their covering groups calculated incorrectly and published. And even as late as 1979, when there was a conference in Santa Cruz, at which the general feeling was everything was collapsing and everybody started to feel down because there was nothing left to work on, and it became kind of clear that the classification really was going to get accomplished. Bob Grice got up early one morning and he nailed what he called the 96th thesis on the door of the lecture room, which said that the covering group of the Matthew group M22 is a 12-fold cover, not a 6-fold cover, which had been previously thought and published. So anyway, I've written, if you don't know what a covering group is, I've written the definition up on top. It's a covering group of G is a group which has G as a quotient. The normal subgroup is the center, and the group is equal to its commutator subgroup, so you're not allowed any cheap extensions like taking direct products. The simplest example is if you take PSLNQ, except for a finite number of cases, the covering group is SLNQ, the actual matrix. All right. Actually, when do I stop?
5:54.
5:54. So now that we know what the simple groups are, we'll just call a K group any finite group, all of whose composition factors are simple known groups. K is the set of known simple groups. And a K group is a finite group, all of whose composition factors lie in K. And a K proper group is a finite group, all of whose proper subgroups are K groups. And if you think about it for a minute, the classification can be restated this way. If you have, by induction, all you have to prove is that if you have a K proper finite simple group, then it's in K as well. And by induction, any simple group is in K. And that's the point of view that the classification proofs that all the classification proofs that now exist take as their point of view. I'd also like to point out that when you have a result as massive as the classification theorem, maybe you need asterisks to put on theorems that use it, and gold stars to put on theorems that don't use it. So I like to make the distinction and call a theorem if it doesn't use the classification. If it does use the classification, call it an observation, because what you're doing is going through the list of simple groups and observing that what you're trying to prove is true. Some observations are a lot harder to prove than some theorems.
So frankly, I like observations better than theorems.
And then there are bootstrap theorems that apply to K-proper simple groups, and these are technical theorems that are used in the proof of the classification. So a bootstrap theorem becomes a theorem once the classification is proved. Here are two examples of observations, one easy to prove, the other hard to prove. The Schreier conjecture says that if you have a non-abelian finite simple group, and you look at the automorphism group always contains the inner automorphisms, the conjugations. They form a group isomorphic to G. If you factor them out, what else could you call it but the outer automorphism group? Even though its elements are not automorphisms, never mind that. The conjecture is the outer automorphism group is solvable. All its composition factors are cyclic with prime group. And not only is that true, as you can observe after the classification, but it's very true. And not only are these groups solvable, they're small. They almost can't get big enough to be non-solvable. So it's still a it would still be nice to have this one be a theorem. I did once have an idea about how to prove it. That idea came to absolutely nothing. But when something is so true, there must be something you think that we're missing.
So there are proofs using classification?
Oh, yeah.
Oh, so
All the automorphism groups of the known simple groups are known, and they're definitely all solved.
So you're looking for a classification of frequent proof?
Yeah. The Sims conjecture is about finite permutation groups, and it's one of his best conjectures, I think. If G is a finite primitive permutation group on omega and a point stabilizer has an orbit of length d, then the size of the point stabilizer is bounded by a function of d. Is it visible if I write on the board? Suppose you have a permutation group G on a set omega. How do you visualize omega? Well, there it is. It's a bunch of points, and the group acts let's assume the action is transitive. The group acts transitively on it. It's a very homogeneous thing. If you take any point and look at it from that point of view, it looks exactly the same as you take any other point and look at it from that point of view. So let's not try to draw the whole thing that way. Let's pick a point and look at the stabilizer of the point. That no longer acts transitively. In fact, it has a one-point orbit, and then it has some other orbits. One of Sims's terrific ideas was to pick one of these orbits and make a graph by connecting the original point to every point in that orbit. And then let the group G act and close it up so that you get a graph that looks exactly the same from any point as any other point. Properties of that graph, it turns out, shed light on the properties of the original group G and the set that it's acting on. And this particular conjecture says, if you take this one orbit and it has size d, then the size of the stabilizer is bounded as a function of d, if G is primitive. If G isn't primitive, it's hopeless. Nothing like that is true. Primitivity means that G alpha is the maximal subgroup of G. It also means that this graph, it can be interpreted by saying this graph is connected, and if you do the same thing with this orbit, that graph is connected, and all the different graphs are connected. That's another way of interpreting primitivity. And this conjecture was proved by Liebeck, Prager, Saxel, and Seitz in quite a long bit of work. I forget when.
Using the classification or without?
Yes, using the classification.
It's an observation.
It's an observation. It's an observation.
But they have one.
People don't like it when I call that stuff.
But he's busy now.
Okay, now let's go on to the next subject. How do you get started proving classification? Well, we've got our K-proper simple group, and it's not of prime order. Thank you. What do we know? Well, we all took Math 551. There's a CELOS subgroup. Let's take a CELOS subgroup, or take any subgroup of it. That will be a subgroup of order p to the a for some prime p. And another simple construction you can do is to look at the normalizer of H. The normalizer of H is the set of all elements of the group that conjugate this H to itself. Conjugation by any element of the group is an automorphism of the group. And if you